Okay, I'm going to begin chapter 1. In the book, chapter 1 is really just kind of a review of the algebra and trig chapter. I also wanted to have us cover Appendix D which is at the back of the book, which is some more essential trig review stuff. Now, of course, algebra and trig are two huge areas in math, and so I'm only going to highlight certain areas from these two fields in this handout. It is critical that you are strong in these two areas, though, okay? After doing this for 15 plus years, my experience with students struggling in calculus is that it's not the calculus, it is the algebra and trig. Okay, they just didn't have the strong background that they needed in those two areas to be successful. So the more that you can practice this stuff, the better. Okay, it's all important. This is all stuff that I've tried to select problems that I think are, quality problems that we will be covering in calc. Okay, and but the more that you can look at, the better. Like anything else, the more you practice, the better. So we'll get right to it. Problem 1, write the slope-intercept equation for a line containing the points -1, 3 and 3, 4. Okay, the first thing that we need to do is find the slope of this line. Change in y over change in x. So 4 minus 3 divided by 3 plus 1 reduces to 1/4. The slope of this line is 1/4. Okay, and the next thing is I could use the point slope equation, and so that equation, we want y minus y1 equals the slope times the quantity x minus x1. It doesn't matter what point we select to plug in the numbers into the point slope formula. I've just selected the first one here. Okay, so y minus y1 is 3 equals the slope we just said is 1/4 times the quantity x minus x1. X minus -1 is the same as x plus 1. Now we're looking for the slope-intercept equation, so we need to give our answer in the form y equal mx plus b. Well, let me distribute the 1/4 here into these two terms on the right, and then I'll add 3 to both sides. 3 is the same as 12 over 4. So 1/4 plus 12 over 4 would be 13 over 4 then. And here'd be my answer. Now, keep the answer, the numbers in exact form, okay, unless you're told otherwise. At the moment, we're doing very little on the calculator, okay. We'll be mixing in some calculator stuff throughout the course, but overall, it's not going to be, a ton of things that we'll be doing on the calculator, all right. Problem 2, okay, we're going to be solving some equations here. The first one is a quadratic equation. I'll get all the terms onto the left. The first thing that you always want to think of with a quadratic is if it factors. This one will not factor nicely for us, no matter what we do with guessing and checking and arranging the numbers. So my next best option would be to use the quadratic formula. And so that's what I'm doing here. I want the opposite of b, which is 4, plus or minus the square root of b squared, -4 squared is 16, minus 4 times a is 2, times c is -3, and this is all over 2a. 2 times 2 is 4. And now at this point, it's just to process and simplify as far as you can go. Underneath the radical, we've got 16 minus a negative, means that I'd be adding something to 16. 16 plus 24 would be 40. And root 40 is going to simplify as 2 root 10. Now I can't cancel these 4s. Some of my algebra students would want to do that, and that would lead to a wrong answer. Okay, you can't cancel because of the plus minus deal that we have here. But we can continue to simplify. If we factor a 2 out from the two terms in the numerator, we can cancel that with part of the 4 in the denominator. Okay, so that's what I've done next. Factor a 2 out. 2 times 2 is 4. This 2 has already been factored out, so that's going to leave you with root 10 there on the second term. 2 over 4 reduces to 1/2. Okay, and so 2 plus or minus root 10 all over 2, that's what I'm looking at now. Just like what I mentioned with the 4s, how you cannot cancel them, the same would be true with the 2s. You cannot cancel the 2s. And so what we see here would be as simplified as we can get it. And again, just leave that in exact form, okay, unless you're told otherwise, exact answers. And of course, simplified, if the radical breaks down or if the expression simplifies, like any other math problem, simplify as far as you can go. Part B, we're going to solve a rational equation. We're going to do lots of things with irrational expressions and equations throughout the course. Now, when you're solving a rational equation, the first thing that you want to do is you want to get rid of the fractional form, or generally that's going to be the plan early on. So to do that here, I'm going to multiply both sides by x times x minus 2. That'll clear out the denominators for me on all three of these. And okay, if I distribute x times x minus 2 into the first term on the left, the x minus 2's will cancel. That'll leave me with 2x plus 1 in the numerator. Also the x that's coming in to that first term there, plus x times x minus 2. When you distribute that in the second term, the x's will cancel. That'll leave you with the 3 that's in the numerator, and then also the x minus 2 that's coming into that second term there. On the right, x times x minus 2, that's the same as x squared minus 2x, which you can cancel with the x squared minus 2x in the denominator. And that'll leave you with negative 6 there on the right. Notice how at this point we no longer have fractions. That's good. We're back on more familiar ground here in clearing those out. So I want to distribute x, distribute the 3, collect my like terms. And if you add 6 to both sides, those terms are gone. X plus 3x is 4x. Okay, and now I've created a quadratic. Remember what I had said a moment ago? The first thing always that you want to do with a quadratic is to try to factor. Now when it comes to factoring, you always want to see if there's a common factor that can be pulled in front. Here, 2x is in common to these two terms, so I can factor that in front. That'll leave me with x plus 2 as the leftover. And I can set these factors equal to 0 now and solve. 2x equals 0 means that x is 0. X plus 2 equals 0 means that x is negative 2. One thing that you always want to do with a rational equation is you got to check your answers. We can sometimes have extraneous solutions come up. And so like here, if I were to plug 0 into the original, then whoops, that'd be a problem, right? With the second term, I know I can't divide by 0. There'd also be a problem over here. So 0 would be extraneous. Throw that number away. Okay, now 2 would be the only other number that would cause a problem here. I'm not getting 2. X equal negative 2 is fine. I don't get division by 0. Of course, division by 0 is not allowed. Okay, so negative 2 is going to be kept. 0 would be extraneous. Part C, we're solving an exponential equation. There wouldn't be an easy way to get the same base on both sides in this one. That's always the first thing that I want to look for in solving an exponential. Can I get the same base on both sides? I can't rewrite 4 as e to some power. I can't rewrite e as 4 to some power, right? So in those situations, we want to get logarithms involved in the calculation. Usually we're working with the natural logarithm. So if I take the ln of both sides, that will allow me to use my laws of logarithms. I know powers can come in front of logarithms. So I'm pulling the 1 minus 2x in front of that logarithm. They're on the left. And the ln of e is 1. So that'll just leave me with 1 minus 2x on the left. ln 4 is just a number. Okay. So let's maybe I'm going to subtract ln 4 and then add 2x to both sides to get to this next line, and then divide by 2 so x is all alone. X would be equal to 1 minus the ln of 4 all over 2. That'd be the exact answer, and I'd circle that. Now, if they were wanting a decimal form, you go to the calculator here. I'm using a TI-83, 84 model is fine. And I'm going to type in, okay, here's 1 minus ln 4, enter, divided by 2, negative 0.193 if I round to the nearest 3 digits. Again, it's not, I don't need to go to a calculator, okay? So, keep it in mind that more times than not, we're going to want the exact answer here for what we're doing. Part D, we're solving a logarithmic equation. A lot of what we do with logarithms revolves around the definition of a logarithm and or using the properties of logarithms. So one property of logarithms says that if you're adding logarithms with the same base, you can combine that to a single logarithm by multiplying the inner terms. And so that's what I'm going to do to get started here. I'm going to get a single logarithm there on the left, and I can distribute the x into those two terms there. And the next thing is I'd want to get rid of the logarithmic notation by applying the definition of a logarithm. Y equal log base a of x means that x equal a to the y. Okay, that's the definition of a logarithm. And I usually tell my algebra students, make sure that you know that. That to me is the most important thing to know when it comes to logarithms, is the definition. There's, so many calculations just revolve around using that one statement. And if you don't know that, that's going to be a problem, for doing a lot of things with logarithms here. So x squared minus 3x is my input. That's going to be all alone on the exponential. 4 is the base, so that would be the base of the exponential now. 1 is my y value. 4 to the first is 4, okay? And if you subtract 4 from both sides, now I'm back on more familiar ground because I no longer have this logarithmic notation going on. And I'm actually looking at a quadratic, right? This one will factor nicely for me as x minus 4 times x plus 1. And so when you set the factors equal to 0, you get x equal 4 or x equal negative 1 as the possible solutions. A logarithmic equation is another kind of equation in algebra where you have to check your answers. You're checking for extraneous solutions. Okay, so let's check these now. You can't take log of a negative. So actually negative 1, I see right away, that can be thrown away. You can't take log of a negative. Also can't take log of 0. So if x is 4, and I plug that in, log base 4 of 4 would be 1. Whenever the base and the input number match up, you always get 1. Okay. Over here, 4 minus 3 is 1. Log base 4 of 1 is 0. Log base anything of 1 is always 0. So I'm looking at 1 plus 0 is 1. That's a true statement, which means that x equal 4 would be kept. X equal negative 1 would be extraneous. Okay, let's take a look at problem 3. We're going to do a lot of things with functions throughout the course. Problem 3, I've got a quadratic function, and we're going to find the following here. Part A, f of x plus f of 3. So f of x is x squared plus 5x minus 1, and I'm going to add f of 3. Well, f of 3 is just going to be a number. F of 3, okay, so 3 squared is 9, plus 15 is 23, 24, and then minus 1 is 23. So in part A, essentially all we're saying is add 23 to the function. Okay, so that's what I'm doing. I'm adding 23, and then I'm going to combine my like terms, the last two terms there. X squared plus 5x plus 22 would be my answer then. Okay, now in part B, f of x plus 3 is different from what I'm being asked to do in part A, because in part B, we're saying that wherever we see an x and f, okay, there's two of them, replace those x's with x plus 3. All right, so let me do that. I'm going to replace those x's with x plus 3, and then I'm going to simplify. X plus 3 times x plus 3, I'll need to FOIL that out, and I get x squared plus 6x plus 9. I'm also going to distribute the 5 here and collect my like terms. So I'm looking at x squared, 6x and 5x is 11x, 9 plus 15 minus 1 is 23. Okay, now notice how these expressions are different. That should make sense. We're doing two different things. On one of them, we're just adding a number to the function, and on the other, we're just, wherever we see an x, we're replacing that with x plus 3. Part C is a calculation that we're going to see a lot early on in calculus, which is called the difference quotient of f. H is a number. H can't be 0, though, okay, because I know I can't divide by 0. But think of H as a number like, H could be 3 or something. So f of x plus h means that where I see x in f, I'll need to replace that with x plus h. There's two x's that need to be replaced. Okay, then I'm going to subtract f of x. F of x is x squared plus 5x minus 1. I'm going to subtract that whole thing. And I would also add, make sure that you put parentheses around that expression since you're subtracting the whole thing. You'll want to distribute the negative into these three terms, and I'm going to do that on the next line here. And this is all over h. Okay, so now at this point, all my information has been plugged into the difference quotient, and now it's just a matter of simplify as far as you can go. We'll need to FOIL out this first part. X plus h times x plus h would be x squared plus 2xh plus h squared. Distribute the 5 into these terms, distribute the negative 1 into these terms, and now combine your like terms. Actually, we'll have some things canceling as well. So x squared minus x squared, those are gone. Here's 5x minus 5x, those are gone. Negative 1 plus 1, those are gone. And so I have these three terms remaining in the numerator. H is in common to all three of these terms in the numerator, so I can take this a step further and I can factor out h and then cancel that with the h that is down under. Okay, and that'll leave me with 2x plus h plus 5, which would be as simplified as I can get it. Okay, and so that would be my answer. We're going to do a lot of things with the difference quotient. You'll see that early on. Okay, the difference quotient is really just a general formula in describing the movement from one point to the next on a curve. Okay, there isn't more to know about that. Okay, especially when we get to the topic of a tangent line, we'll be using this, a lot. So we want to make sure that we are good with computing a difference quotient. Right? And I'm going to go ahead and stop the video right here.